Yes, good morning for the people that live in California, and good day to you for the rest. So I'm going to talk about two parts. Actually, let me say it another way. This talk has two parts, right? So at France, we've had so much fun in the last 1.5, 2 years playing with LLMs, right? And I guess most people in the audience have played with that. And so we wanted to create some capabilities in AllegroGraph so that you don't have to use any LangChain or any other system. You just could do all your interactions with an LLM directly from Sparkle and directly use that to create knowledge graphs or curate knowledge graphs, right? So the first part of my talk will be just go through a list of magic predicates that we added to Sparkle so you can directly interact with any LLM that you want. And then the second part of the talk is something that also excites us very much, and that is this new capability of neuro-symbolic artificial intelligence. Just to summarize, right, we have a knowledge graphs, but for the last 15 years, we've been doing logic, right, with knowledge graphs, and then about 10 years ago, everyone started using classical machine learning with knowledge graphs, right? We did event prediction, classifications. But then for the last 2 years, we added LLMs to our knowledge graph and LLM capabilities. And the interesting thing is that each of these three AI systems that I just mentioned have incredibly strong parts, but also weak parts, right? And we created a platform where you can use all three types of AI at the same time and use the strength of one system to remedy the failures in another system, right? So that's what my talk is going to be. How can I mix all these AIs together using the knowledge graph as the glue and the controller that binds everything together, right? Okay, so let me dive in. So first about these magic predicates. So this is the list. We have more than what you see here, but I'm going to talk about LLM response, where you just ask a question and then force an LLM to return a list of elements or JSON structures or just a string, right? And usually we get strings back, and sometimes you need a reliable way to take a string that you get back from an LLM and turn it into an IRI. So we have a function for that. And just with these two, you can do amazing things. I'm going to show that. But sometimes you can shortcut all of this and just ask an LLM for a table of results, right? And make it very easy to get complex information in one go. So that is just using an outside LLM. But we also embedded a vector store in AllegroGraph, a fully transactional ACID vector store. And we have two predicates I'm going to discuss. One is LLM Ask My Documents, where you can ask questions against your own documents that you stored. And an LLM Nearest Neighbor, if you just want to find, given the input string, the text in your vector store that are the closest to what you were looking for, right? So that is, I'm going to talk about that. And then finally, this is in research, but I wanted to mention it anyway, is we can now also build future completely stateful bots to mix local expertise that you might have in your own vector store with a history of a conversation that you might have via a series of Sparkle queries. And we even get to the point where we're working together with a psychiatrist to build ELISA 3.0. Anyway, this is the set of magic predicates that I want to discuss. We have this function called response, where you can just ask any question you want to an LLM, right? And you get a response back. So in this case, hello GPT, and the response is, hello, how can I assist you today? And you think, well, is that all, right? But this is almost like lambda calculus. This is almost all you need to do anything you want. But let me explain. So, right. So here, oh, this is, by the way, just a little sidestep. But so we have the response function, and within the response function, I could even write a Sparkle query, right? So here I have a Sparkle query. Then within the Sparkle query, I say to LLM, right? Write a Sparkle query to extract 10 city out of DBpedia, only to return the Sparkle string. Include the prefixes as response, right? And what you would get is that it will write a Sparkle query that you could execute, right? So this is
This is only for people that are deep into programming excursion and maybe Lispers, right? Where you do recursive sparkle generation. Anyway, this is just a little side issue, right? Now let's look at LLM response as a magic predicate. So here we can say, give me all the entries, right? Well, LLM response, list the US states, right? And I get a list of 50 states back. And well, you can try anything you want. So we have, this is part of our web interface to 8.0, where we have a playground where some of these queries are all listed. So you can just go to our playground and play with that. But I hope you get the point, right? I do LLM response, list the US states. We do the function calling for an LLM, say you're using ChatGPT, right? To make sure you get correct list back that we then can do something with. So then the next thing is, so say I asked for a bunch of states, right? But that's just a string. And in many cases, you want to build more information around the string that you got back. So you have to turn that string into an IRI. And if you have no other help, you want a reliable method that, given this string, you always get the same URIs. And that is what the function LLM node does. Yeah. So if I say LLM response largest US state, name only, a state, and then you say this state becomes a node, right? And then here you see that Alaska will always have the same URI. So you can work with that. All right, so this is the basics. And then that is infinitely composable, right? So say I wanted to have for every state in the US, the name, the capital, the population, the area in square miles, when I was admitted to the union, the current governor, and an important celebrity, right? Well, I would first say, give me 10 states, right? Just to make, because this is going to take time, right? When you talk to an LLM. And then you say, okay, well, name the capital of the state that you returned here. Return the city name only as capital. And then you say, state the population of this state and respond with the number only as population, etc., 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 right? To get all the way down to the point where you have all this information. And here is a table that you get back. And you can imagine that if I did this with an insert statement, I could instantly build up a knowledge graph, right? With key information about particular states, right? I hope you get that from this tiny little example. But I mean, this is a lot of work to type, right? And but it's incredibly flexible, but it's a lot of work to do. So that's why we also invented a magic predicate that we call ask for table, right? And so in this case, we say select state, capital, population, area, admitted governor, and celebrity, right? And here you have a bunch, and then you say to the LLM, ask for table, make a table of US states, the capital's population, area, year admitted to the union, current governor, the most famous celebrity for that state. And then the LLM will literally come back with a comma-separated file where we leave off the top, right? And it will bind these variables on the left-hand side of the magic predicate to the header of the variables in the comma-separated file, and boom, you get your response again. So this is very easy, right, to create this particular table. And so I can do many, many, many different things with it, right? I mean, I've given several talks about how you can create ontologies of a wine knowledge graph. I have demos where I can show how to create any wine palette or the wine, the various flavors that you might have in the wine. But here's a very simple example of ask my table is create a table of the top 4 types of wine, the 3 major wine types of each type, 3 vintages of each wine type. And the table should have so many rows, right? And this in the query. And then I also want to have a review of each of these wines. So again, I can insert the review. And then here is just a tiny part of a knowledge graph, right? It's a root, sparkling wines. Cava is one of the sparkling wines. And here are a few vintages of this. And in this can we also have, let's say, a few reviews of this particular wine. I hope this makes sense, right? And again, today is not the time, but I could give a whole hour a talk just talking about a wine knowledge graph that we had built up with several million triples. Okay. Another really interesting demo is, so I always say that an LLM like ChatGPT or a Llama or what have you are basically knowledge graphs in themselves, and you just have to extract the graphs out of these knowledge graphs. So here is an interesting example where I say, okay, well, list the US states, right? And then also for each of the states, write the states that border this particular state, right? And then I make that the prompt. And then I get the borders and their nodes back from this border prompt. And I delete relationship between states. If so, state 1 should point to state 2 and state 2 should point back to state 1. But I only keep the ones when they both have list each other as neighbors, right? Sorry for my chaotic explanation here. And so once I have that, right, I could do a Sparkle query, right? I can say select SO where this state borders this O, right? And I get this, but of course it's more fun to click on Visual Graph. And here you see the a part of the graph. And the interesting thing is, because of the way this works, if you do a spring layout, you already instantly get the kind of the shape of the United States that you see here at the left bottom, right? So you see Washington, Oregon, California, then Nevada and Arizona. And it's kind of really interesting to see how the graph follow. Anyway, you get my point, I hope, right? So here is the whole graph. Here we have Washington and here we have Maine, right? And one of the things we could do is also use in graph our tree layout, right? So I like this actually better, right? So here you see a rendering where you use the shortest path as the way to organize your graph. So we get all the way from California to Maine. If in graph I put my mouse here, you see the shortest path from here. And you see you need 11 steps to get from Maine to California. If I ask that question directly to ChatGPT, right? Imagine a graph where each state in the US is a node. And for every state that borders that node, there's a connection between the nodes. List the nodes in the shortest path from Maine to California. And then it kind of screws up, right? Because it takes 14 steps to get from Maine to California, right? So again, there are graphs in the LLM if you just know how to get them out, right? But of course, an LLM is not a graph database in itself, right? And you can't do the shortest path. I'm saying cannot, right? Probably in 2 years' time it can do that too, right? But for now it can't do it. All right, so this is an interesting way, I think, right, to extract a graph out of an LLM. But let me continue. So also, let me hide the video panel here. So we always talk about hallucination, hallucinations with LLMs, right? And how you can get rid of hallucinations, right? And I'm first going to give you an example. And the example is where I ask for to create a knowledge graph with the 10 most expensive cars and their price according to LLM and Google, right? So first, what I do is I asked in Sparkle, and this is in the Sparkle query here. I hope you can see my mouse, right? So I say, ask my table, list the 10 most expensive cars and their prices as integers. And just to make life easier, format the integers without commas, omit table header, right? And once I have that, I have 10 cars with their prices. But who knows, is the price correct or not? So I do another step. I ask SERP, which is an API to the Google search engine, to also ask for the price of the 10 most expensive cars, right? So I say, ask SERP, an LM, it's not an LLM function, except it's going to Google, it's not really an LLM. Find the price of the Bugatti Veyron, right? And I get an answer. Now the problem is that SERP doesn't give, SERP gives you back a JSON object, and sometimes when you ask for the price, you're lucky and you get the price, but most of the time you just get the piece of text back, and somewhere in that text they have hidden the price that you were looking for, right? But the problem is that it could be 80M or 80 a million spelled with commas or without the commas. Anyway, there's many ways you can do it. And initially, I tried to use Spacey, right, this Python library to do a NLP to extract the prices, but I gave up. And basically, I then ask the LLM again to read. So I do the next step in the LLM. I say, extract the price of the car as an integer from the following text, which came from SERP, right? And then respond with the integer only, blah, 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 right? So here, within one query, right, I talk to, here, I hope you can see my mouse. I talk to Google to get the price back. And then I use the LLM to get the price of the car actually out of this, right? But I hope you see the beauty of this scheme. And then I have to signal that there's a hallucination, right? By the way, I get extremely, well, kind of irritated when people talk about LLMs hallucinating, right? Because how often does Google itself hallucinate when you ask for something? And even while I'm talking to you, I probably hallucinate a few things that I'm saying, right? And if you look at machine learning models, they will hallucinate. They will be biased and give you sometimes the wrong answer. And LLMs too. So I don't know why they single out LLMs so much for hallucinations. But anyway, having said that, right? In this case, let's not see who hallucinates, whether it's the LLM or Google, but just signal if there's a difference of more than 20% in price, right? And so here's a simple Sparkle query to insert an hallucination object in the graph if there's more than 20% difference. And then if I look in graph, then I see the little knowledge graph that I built up. So there are 10 cars here, and then each cars have a SERP answer, which is this color. Sorry, the SERP price, which is this kind of purple color, and the LLM price, which is this bluish color, right? And so here, for example, you see the Bugatti, right? It's according to SERP, it's, well, this weird number here. Let's see, it's $113 million, and it's only $25 million according to the LLM. And this is according to Google. Anyway, so once this happens, I create an hallucination object, right? And now I can work further with this one. I really wish we were in an audience together, and because when I give this talk, people have so many questions about this. I hope just me talking to a screen is enough for you to get it. All right. So then these are the things that we did if you just want to talk to an LLM that is on the outside, right? But what if you have your own vector store? What can you do with that, right? And I'm guessing you guys by now all know how a vector store works, right? So in our case, you have a knowledge graph with unstructured content. And then embedded in this one, we built this vector store. So basically, when you say have a clinical trial with text, right? You take the text, you give it, you take out the index tag fragment, you give it to an LLM that's specified in embeddings, and you turn the embedding vector back into the vector store. And then when I do a query, I first go to the embedding LLM, then I find the nearest neighbors in the embedded vector store, and then I get the text fragments that belong to the vectors that goes into the prompt, right? And then the prompt goes to the LLM, and the LLM will give you an answer, yeah, an answer back. But the cool thing is, if you do this in the knowledge graph, it will also give you back the references to the fragments where the answer came from, right? So it's not just giving you an answer, but the exact part of where the answer came from. Anyway, so that is for RAG. So let's just take this example of having Chomsky, of having a database, a knowledge graph with books, right? So for example, I take all the books by Noam Chomsky, right? One of the chapters is public relations. Within that, there's a paragraph, and in this paragraph, right, there's a whole bunch of text, right? And in the old days, we would extract the entities out of this paragraph, and then we would, for example, find that there's a correlation between South Africa and Nelson Mandela, right? And it is very high, but the point is, what we can do now is we take the text, right, and we put these text fragments in our embedded tuple store, vector store, right? And now I can do a query like ask my documents, right, where you say, if the query is what policy would you suggest to reduce inequality in America, right? Then you would just say you would use this magic predicate ask my documents, right? And it would return a response. And the citations or where it came from and the score for this particular citation, how much you believe it, and then the content, right? And then here would be the query that you just created there. And this is the vector store where that you want to use, right? And you say, base your answer on the 10 top best fragments, right? That you could use for, anyway, you get my point. And so here is the response, right? To reduce inequality in America, policies should include a wealth tax, increase minimum wage, stronger labor rights, blah, 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 right? But I hope you see what the beauty is here. You get your answer, but you get also the parts in the books that I showed you here, right? The paragraphs in the book that you based your answer on, right? So that's what you can work with then. Now, sometimes you don't want to write a full Sparkle query for all of this, right? So in 8.1, the version that real soon will come out, hopefully, well, almost certainly this month, you can also just type your queries, right? And what the main causes of poverty, and then without doing any Sparkle questions, you get your answer, and you get the citations and the content and the confidence level for these citations. I hope this is clear. Right. And then another new thing that's going to be in our next release of AllegroGraph 8.1, right, where we actually can also do stateful chatbots, right? For example, what we now have is you need two vector stores to work with this. You need a vector store that has expertise about a certain area. Just think of, say, you're building a psychiatrist, right? And the psychiatrist meets the person over multiple sessions. So what happens is that while the psychiatrist is talking to the patient, every time in a session, the whole session goes in fragments to the expertise, goes into the history for this particular patient. And the psychiatrist that we're working with also has thousands of conversations between him and patient, by the way, completely made up, but as examples of how he responds usually. And then we can then do something like create use this function or this magic predicate LLM chat say, there's nothing you can do for me, right? Use this expertise database that I found here and use this history database from here, right? And then you get an answer, right? I understand that you're feeling this way and I truly empathize. You might remember in our previous sessions, we talked about how any complex problem can be addressed by dividing in manageable parts, right? So it's going back into the history. So it looks both, actually I can show this better here, right? So we have a history of all the previous sessions, right? And when we get a query in, we match it against the history, we get history matches. That gets then summarized into a history hints. But there's also expertise that a psychiatrist has, right? So this is the vector store, and then we match the query against this, and we find the matches here. So here's the expertise hints. And then, of course, you have the current dialogue for today, which then gets summarized into a story, and all of that ultimately goes into a prompt. Now, if you want to look at all the intermediate variables that we use, the score, the source, the feed, the story, the expertise match string, blah, blah, you can, and sorry, it's hard to read probably on your screen, right? But you can have a look at each of these various parts that you need to ultimately create an answer. Anyway, we want other people to play with this, so contest for help if you want to experiment with this chat shade thing. I think it's an amazing new technology. We'd love for you to use it, so contact us. All right, so this is the first part of my talk. So now let's go to the second part, right? So I've talked how we can talk in AllegroGraph to vector stores and LLMs and combine it all in meaningful ways. Now let's go a little bit deeper. Sorry, not deeper, but in higher up, right? So this part of the call is now about neuro-symbolic AI. So I am a psychologist, and I did my thesis in cognitive science, and I modeled a car driver, and I wrote several thousand rules to model a car driver driving in traffic. And when I wrote my thesis, I already, in my thesis, lamented the fact that machine learning wasn't there yet, and I couldn't do, say, object recognition, right, in a simulated world to help with my model, right? So I'm really happy to see now that in recent times everything came together, right? And now I can use both logic and machine learning for almost anything I want to do. So in 2021, I started writing about neuro-symbolic AI, right? Or what we call composite AI, where you use various types of AI to make your inferences better. And in 2023, it was picked up by Gartner. I mean, I was not the only one writing about it, but there's Gartner kind of picked it up. So it's on the hype cycle. So now we know it's really real, right? And Gartner also kind of talks about why they think it's so important, right? And we would say that the most important drivers for neuro-symbolic AI is trusting your data. And I talked about it when I started, but let me say it again, right? LLMs hallucinate. Machine learning models have biases or not always give you the right response. And logic is also not always the answer, right? So, but if you can get these three types of AI to work together, right, you might trust your data more. And also, if you use these three types of AI systems together, your data might also get way more explainable, right? So you might be in a hospital situation and you have a beautiful machine learning model, a recurrent neural network of a convolutional model that does fantastic predictions, but you just don't know why, right? Well, an LLM could look at that particular patient for which you have a prediction and explain to you why this might be the case, right? Anyway, so that is trust and explainability are the main parts, of course. And then, of course, you always want to have the semantics, right? I mean, if you live in a machine learning world only, right? And I mean classical machine learning, not the new LLM stuff, right? Again, you can't really talk about anything. You need semantics to make things to get real entities that you can talk about. So let me stick to that one here for now, right? And so we make this claim that AllegroGraph is a neuro-symbolic knowledge graph. But what do we mean by that? Well, let me explain. So when our knowledge graph industry started working, right, and we started about this 15 years ago, we already were 100% symbolic, right? So we had ontologies and taxonomies, and we used description logics. And then we at AllegroGraph also have a fully functional compliant Prolog compiler built in. So we also can do constraint-based reasoning, multi-step planning, what-if scenarios, things you really can't do with the machine learning model, and something that LLMs are not yet ready for, right? So this is very cool stuff. And now let me take a step back, right? So this is the symbolic stuff that we've been doing for a very long time, right? And then for the last 10 years, right? Almost any knowledge graph that we built had a machine learning component, whether it was for airplane maintenance or predicting customer choices or predicting diseases, right? We all had it, used machine learning for that. We did graph neural networks, we did recurrent neural networks, we did classification of entities, anomaly detection, right? And linked it very closely to our knowledge graph. And then recently, right, in the last 2 years, we had this amazing explosion of AI, right, using LLMs and vector stores, right, where we now can use entity and event extraction on the local and structured content in our knowledge graph. We can do query answering on both on local and remote knowledge. We can do any kind of symbolic reasoning, prediction, explanation, causal chains, etc. Right? So we have this knowledge graph and we have all these technologies around it. So let's go a little bit deeper into, okay, the strengths and the weaknesses of each of these three systems, right? So, and I won't go too deep here, but I mean, so first let's look at logic, right? Or the symbolic logic. I mean, if you can use rules, right? The rules can be extremely precise and they're very deterministic and consistent. So I mean, it's if you can do something with a rule-based system, I always say, please do that, right? Because and it's the most consistent thing you can get. But the problem is, and I don't know if anyone in the audience had done it themselves, but if you write a system with 2,000 rules, like I did for my driver, and then you add rule 2001, well, that one rule has so many opportunities to interact with all the other rules, right? That before you know it, then you're debugging for hours and days, right? To add this one more rule to your system. So, and then of course, the world is always changing. And every time you want to deal with a novel case, you have to write more rules and it gets more and more complex. So so the strength is it's precise, consistent, transparent, and explainable, but it's really hard to maintain and complex. Then machine learning. I mean, when we started working with machine learning, it was almost like magic, right? You give it the right feature sets and it will learn and adapt from your data without writing any rules. And it can apply to a very large data set and learn all kinds of patterns that you might be interested in. But on the other hand, and we've seen this as a real problem in several domains, we have the black box problem. We just don't know why the machine learning took a particular made a particular choice, right? And then there's always the data quality and the quantity issue, right? I mean, garbage in, garbage out, and then there's the ethical issues, right? So I'm actually from the Netherlands, and about 4 years ago, the Dutch government had to 3 years ago, the Dutch government had to resign because they were using a machine learning model at the Dutch IRS to figure out whether or not certain people might be cheating on their child care funding. And that machine learning model was chock full of biases against ethnic minorities, right? And so basically, anyway, you get my point there. So this is for machine learning. And then we have, of course, LLMs with their strengths and weaknesses. I mean, it's amazing in what it can do with natural language understanding. I never thought as a psychologist that we could get to this particular point, right? But there's always these hallucinations. I never, ever trust anything that comes out of an LLM, right? I always have to double or triple check, right? So this is the strengths and weaknesses. And I'm sure almost anyone in the audience knows about this. So people started writing about how can these systems make each other better, right? And we found this beautiful article in Science Direct, right, where someone describes really well how you can have a symbolic knowledge graph with knowledge. You use the symbolic knowledge graph to create embeddings. So now you can change you can add it to your machine learning models. The machine learning models will start learning and it will learn new patterns, new rules. You can extract those from the machine learning models. There's a lot of new software that can help you with that. And now I changed my symbolic knowledge graph and then I can maybe make new embeddings, right? So this is a beautiful picture of how people try to have these systems make each other better. But this is only symbolic knowledge graphs and neural. I was kind of tempted to put in one more thing here because what I found is that you can even ask an LLM to create a feature vector. So if you ask an LLM, hey, what are the features I need for a machine learning model to predict whether or not someone is going to get, say, a disease like GERD, and then, right? It will both create a feature vector for you based on the content in the knowledge graph and the Python program to run it, right? So another example of how these systems can make each other better. And so we in AllegroGraph, right, created this framework, right, where we can talk to the LLM, and I showed you that in great detail and in the past, and you know we can do the symbolic reasoning, right, because that's what knowledge graphs do. And then we have the machine learning frameworks that we can talk directly to from our knowledge graph. For example, if you anyway, we can do neural networks, take the output, feed neural networks directly from the knowledge graph. So we have these systems. And so if we, for example, apply this to healthcare, right? Then, and I'm going to talk about this in way more detail, but say I have a healthcare knowledge graph with patient information and taxonomies and all that, right? I can start learning based on all the events for all the patients using recurrent neural networks and then use that to predict future events. But I can also predict future events by taking a sequence of medications, diseases, procedures, observations, tests, feed it to an LLM, and based on the fact that it read 36 million PubMed articles, it will also come up with a prediction, right? And of course, I can do this in symbolic information. I'm going to talk about it in a minute, right? So the example I'm going to talk about, I've talked about this before, and I'm not so much interested in talk about healthcare today. This healthcare knowledge graph that we have is one of the best playgrounds, right, to take all these technologies and see how you can mix and match them all together. So for years, we worked with a hospital in the Bronx, where we had 3 million patients in a knowledge graph using an entity event knowledge graph model. This is an article that came out in 2022, where we describe the benefits of this particular event modeling system. And this was a great model, but the problem was that we couldn't show this to anyone because it had patient data in it. So what we did is we took the patient data out and filled it in with or synthetic data that was created by MITRE. It's called Cynthia, or we inserted Mimic, which is anonymized data in this knowledge graph. And now we can give this to hospitals, right, to play with our knowledge graph in about 10 Jupyter notebooks, with any kind of analytics you can think of, right? So you can practice working with knowledge graph to see if you really like this particular thing, right? So anyway, I actually provided DALL-E in my ChatGPT with an abstract of this paper, right? And said, can you make a visualization of this? And it came up with this beautiful visualization. And so I'm keeping this one, although I also have a more psychedelic version, which most people like even more, but I think this one looks a slightly more business-like, right? So anyway, I'm kind of really enamored what I got out of DALL-E for here. Okay, so now let's talk about my healthcare example, right? In terms of this neuro-symbolic AI healthcare. So let's begin with how can I, for example, diagnose or prescribe or report or predict using symbolic reasoning, right? So I'm going to show you in a minute, but we can, let me take a step back. So we have this disease called GERD, right? About 20% of people in the United States have this problem, what they call gastroesophageal, I can't pronounce it, reflux disease. I call it GERD, right? And here is a simple logic program in Prolog, right, where we can predict whether what someone's risk level is for this particular kind of disease, right? And we might have some facts that the patient is obese and smokes and has frequent heartburn, blah, blah. And then we could say the risk level of GERD for this particular patient is high if the patient is obese and the person or smokes or has hiatal hernia, and he has or frequent heartburn or regurgitation and eats large meals, right? Well, then your risk level is pretty high, right? So this is using a symbolic system to predict whether or not you might get GERD, right? And this reflects also in some way how doctors actually think about it. I can also use a neural network, right? I can take in my knowledge graph all the people that get GERD, take all the events that led up to this, and then take a control group of patients that look demographically like these patients, but did not get GERD, right? And then train a recurrent neural network, and then we can predict whether or not someone is going to get this particular disease, GERD, right? Or I can take a sequence of events for a particular patient and then give it to the LLM, and then based on the medical history of this patient, right? I get also a prediction. I don't want to go too deep in there because otherwise it would take way too much time, right? So all these three things can predict GERD, right? Now, how can these systems make each other better, right? So I'm just going to go through this fairly quickly, but an LLM can explain the machine learning outcomes, verify predictions from the verify the predictions, or do even feature engineering, right? And an LLM, right, can also make the logic system better, right? So it can ask for more facts before committing to a prediction. But actually, the logic that I just showed you, this logic, was written by an LLM, right? So I asked, and this took only a little while, and it wrote a full functioning Prolog program, right, directly from the LLM. Now, where am I here? I'm here, right? So it wrote actually a logic program for me that then doctors can apply directly. And then how can a symbolic system help an LLM, right? Well, or work with it? Well, I can ask the LLM for diagnostic help, but I can also feed the LLM with the medical history. Then a symbolic system can create the feature factors and the event sequences from machine learning. And a neural network can, say, for example, test the efficiency of clinical care plans. I mean, this is endless, right? I just try to give you a few examples of what you can do, but I hope this makes sense to you guys, right? So a few seconds, let me just make this slightly more understandable for you guys. And let me talk about this thing that we call patient graph again, right? So this knowledge graph that we started with the hospital, and then where we took out this the actual patient data and put in the simulated data, right? Or the anonymized data. So in this system, we have 350,000 clinical trials from the FDA website. We have about 100,000 PubMed articles, mostly COVID related. We have the adverse effects of vaccines, and we have electronic medical records from Cynthia or from a data set we call Mimic4, which is anonymized data, right? And at the heart of this is UMLS, right? So you might have heard of UMLS, but it's all the taxonomies in healthcare. They include we have about 180, but here are the biggest ones. ICD-10 are the billing codes, the procedure codes, and then we have, for example, the terms for clinical drugs, et cetera, right? And then everything harmonized with what we call the meta thesaurus. So this is the UMLS. And then because 80% of all the medical data in our knowledge graph is unstructured, I mean, you couldn't do really very intelligent queries. So we had to use an LLM. In this case, it was BioBird, right, to extract all the medical terms from PubMed and from the clinical trials and from the electronic medical records and the and this database, right, and harmonize it. And that means that we now have this model where, say, this is a patient. This is the medical record of one patient. So this patient had an encounter. Could have 1,000 encounters, but one encounter with a condition, acute viral pharyngitis, right, which links to an ICD-10 code, acute pharyngitis, which then links to UMLS into SNOMED or the meta thesaurus, right? So here you have the taxonomy tree for pharyngitis, right? But we also have clinical trials. So here's 2 clinical trials that both talk about acute pharyngitis, right? Here's the short summary of these clinical trials. And we have PubMed literature, so 2 articles from PubMed, again, talk about sore throat, which relates to pharyngitis. And then we have the FARS database that, again, talks about sore throat, and which is related to pharyngitis, right? So within one knowledge graph, we have linked all these data sets together. But the really cool part is here, right? So talking about neuro-symbolic AI, you think, so how does it all come together in the knowledge graph? Well, here is how it comes together, right? We have what I call the symbolic reality, right? You have a patient, that's the demographics and encounters, like this encounter has sinusitis, this person, right? So here is the symbolic reality. But we have a process, a pipeline, where I can take the sequences of events for, say, this particular person and all the people in the database, right? Train an RNN, and now I can actually predict whether this person is going to have GERD, right? So here's a prediction. So this is an event, just like this event here, but in this case, the event comes from an RNN, and it's 0.286 certainty that we'll get this. There's more information here also about the time frame when you think you're going to get it. And here we see that the LLM looked at the sequence of events and also came up with a prediction that this person is going to get GERD, but it also gave us a reason why this might happen, right? And it's a little bit more certain than the machine learning model that this is going to happen. Now, once you have this, right, so I hope you understand how the knowledge graph ties everything together, right? So you have the symbolic logic, right? You have the LLM and RNN, but where it comes together is that you store the output of these various systems in the same knowledge graph, because that gives you then a handle to do other things like find the cases where the LLM and the RNN both predict the same breathing plugs for the same patient, right? And you could click here and then you would find, but you can also find when they not are the same, right? And yeah, again, I wish I was in an audience where you guys could ask questions. That would be better, but I hope you get the point, right? So how a knowledge graph literally ties all of this together into one system. And that was literally all I wanted to do for today. So thank you for your attention.